It's really my great pleasure to introduce Professor Moshe Vardi as one of our keynote speakers. Professor Vardi is a legend in logic, theoretical computer science, and formal verification. He really needs no introduction, but allow me to continue. So he's a university professor and the George Distinguished Service Professor in Computational Engineering at Rice University. And he has received many, many awards. I'm going to highlight the most important awards. He was the winner of the Gödel Prize, one of the highest awards in theoretical computer science. He's the winner of the ACM Sigmod Cod Award, the Blaise Pascal Medal, the Siglog Church Award, Alonzo Church Award, the Knuth Prize, Alan Newell Award, Norbert Wiener Award, etc. He has authored or co-authored over 700 papers about reasoning and knowledge, finite model theory and its application, formal methods, etc. And he's a member of the US National Academy of Engineering and National Academy of Science, the American Academy of Arts and Sciences, European Academy of Science, and Academia Europaea. He has 7 honorary doctorates, and he completed his PhD from the Hebrew University in Jerusalem in 1981. Without further ado, Moshe, the floor is yours. Thank you.
Thank you. Thank you for this kind introduction and for the opportunity to address you today. Vijay, our discussion gave me an idea that maybe instead of counting publications, we should count submissions. then I probably have like, who knows, 2,000, 3,000 submissions, who knows?
But still, being able to write that many submissions, that's also an achievement.
Okay, so I want to talk to you about linear temporal logic, a very classical topic in formal method. And I want to tell you about the development of the last decades, but going from infinite to finite horizon. But let me start with kind of a more general background. In 1985, Harel Pnoeli wrote a beautiful classical paper describing the concept of reactive system. And they point out that there's a class of program, also sometimes people call them open system, that what characterize them is ongoing interaction with the environment. And in fact, many of the programs that we use are of this nature, okay? We write very few programs to compute how much is 6 times 7, okay? But we use, when I give a talk, it's an interactive, I'm interacting with my laptop, okay? So this is the feature. I'm going to take a toy example, kind of give an example of reactive system, which is a printer. I want to specify printer. So there are a proposition J1 and let's say J2, or how many jobs is say a job is submitted, and PI says that a job is printed. And these are kind of very simple specification. We want that not 2 jobs will be printing at the same time. That's going to be a mess. And every job submitted is eventually printed. Okay, that's what we would like. And these are behavioral requirements. I mean, you kind of have to keep in mind that when you look at the program verification, all the way from Turing until the mid-70s, people say program take inputs and outputs. So the specification is always about the relationship between input and output. And now we say, no, we need to reason about ongoing computation. So it's a different style of specification and of course, verification. And the concept was really in Amir Pnoeli's mind in the mid-70s. And he introduced linear temporal logic, which is really a logic that was introduced earlier by philosophers, by Prior in the 50s. But Amir Pnoeli said, this is the right logic to talk about ongoing computations. And it's propositional logic enhanced with temporal connectives, next, eventually, always, until. And it's interpreted over infinite traces. That's the way Amir Pnoeli introduced it. Why infinite traces? He says, because, my operating system in principle is supposed to run forever. Of course, it will, after, who knows, 3, 4, 5, 6 years, it will be obsolete. But in principle, it's supposed to run forever. So let's take this idealized approach, which is infinite traces. So I'm assuming that you're familiar. I'm just going to give you a picture. If I want to say the notation is trace pi, state W, point W, satisfy, double ternary satisfy next phi, if you go 1 point after W. So you go, this is W, and we go one further point and phi is true. Until has an real ongoing semantics. If you say phi until psi, then phi should be true until psi is true. Again, I'm just hopefully reminding everybody what is LTL. So here are kind of classical example. You want to specify safety. Example of safety, we say the two jobs are not printing at the same time. Always not CS1 and CS2. CS1 and CS2 are critical section 1, critical section 2. Okay, so this is a safety property. Liveness properties. Liveness means that good things should happen. So always request implies eventually grant. This is one example of liveness. Another example of liveness is request implies that request stays on until we have request until request or grant, and this is weak until here. Okay, and liveness also could mean if you have infinitely many requests, then eventually you'll have a grant. So these are examples of properties of safety and liveness. And going back to the printer example, safety would say always not P1 and P2. Again, this is again the mutual exclusion. And liveness would mean every job is eventually printed. So always conjunction J equal 1 and 2, Ji implies eventually Pi. Okay, so these are the an example of using these properties to specify reactive system. Now, the traditional application has been for using LTL properties in model checking. So what happens in model checking? We have a program P and a formula phi, which is specify the desired behavior. In model checking, we check that P satisfies phi. So this is the task. We want to know that all behaviors of P satisfies phi. And of course, one of the major accomplishments in our field is the fact that model checking is a problem it's decidable. We can solve it algorithmically. We are focusing on finite set programs, and there is an algorithm that tells you whether P satisfies phi or not. Some extension to infinite set program. For example, if you have a simple recursion, simple form of recursion, you can also prove it. Classical tool like SMV and Spin and SLAM. And today, in fact, there are many industrial tools. If you go especially in the EDA industry, electronic design automation, the semiconductor industry, there are large EDA company. They all have model checking tools that they provide. However, as people, the success story in the application of model checking, people discover that yes, it's nice to have automation in verifying and finding bugs in program. The nice thing about model checking, when model checking fails, you get a counter example. It's very useful to debug the program. But first, you have to write the program, or this hardware design are really programs in a particular programming language called Verilog or VHDL or System Verilog. Coding is hard, we know that. What happens when you find a bug? So actually, it's much, again, if you talk to people at CAB, they say, oh, we give you counter example. Counter example doesn't tell you what the bug is. It just says, here is incorrect behavior. There's a whole issue of root cause analysis, finding what is really the bug, fixing the bug. This is all long, slow, and agonizing. So another idea that has been floating around is the idea of let's automate the design process. That says, if we have fully specified the program by writing enough LTL property, why don't we design P such it is correct by construction? We have the properties. Why can't we use them in the design? So now we don't need to do verification. There's no debugging. It's just correct by design. In fact, what we would like to have is algorithmic design by algorithmic correctness by design. That is to say, a compiler that goes from LTL properties to program. Now, of course, people say, how do I make sure there are no bugs in the specification? You cannot. Okay, ultimately, there's always a gap between what's in your head and what's on the paper. Okay, I still make, I still sometimes mistype my name, even though I know how to spell it. Okay, this happens. But we are raising the level of abstraction. It's declarative programming taken to the limit. You don't need to specify program, you specify the properties of the program. And David Darrell wrote a nice article in 2008, can programming be liberated, period? People talk about liberating programmers from this and from that. And he said, can we just be liberated from programming? Can we instead focus on essentially what's called in software engineering, requirement engineering? Write the requirements, formalize them, you get the program out of it automatically. Now, this is an idea that goes back to 1969. Interesting, because 1969, it was also the year that Tony Hoare wrote a famous article, The Axiomatic Basis of Computer Programming, which was the really kind of culmination of many years of putting foundation for verification. But the same year came an idea of the so-called mechanical translation of a human understandable task specification to a program that is known to meet the specification. Now, when the first paper were written by Green and Waldinger and Lee, and then by Mann and Waldinger, they were still thinking about classical programs that transform input to output. So what is realizability? You write, first of all, what you want to say is for all X, for every input X, there exists output Y, such as if X satisfies the precondition, then Y satisfies the postcondition relative to X. This just said that you can realize the specification. So their idea was prove the realizability of the specification, and from that proof, extract a program. So this is a very nice idea how we can take a proof and extract the program out of it. So this was classical synthesis. And from this, we developed temporal synthesis. Now, instead of doing input-output programs, we're talking about synthesizing program for ongoing computations. Okay, so we have now temporal synthesis. We synthesize program for ongoing computations. So around 1980, people start talking about synthesis of ongoing programs, where the spec is given to in terms of LTL formulas. And at first, the idea was, let's do synthesis via satisfiability. How do we do that? Give me the specification, the formula, check if it is satisfiable. If it is satisfiable, you can get not just yes, no, but you can get a satisfying model. That model should be viewed as a program. And for some specification, it actually works nicely. Here is the specification. Always odd implies next not odd. And always not odd implies next odd. Is it satisfiable? Here is a model that satisfies it, which is you just flip between odd and not odd. And you see that this is essentially, we have synthesized a 1-bit counter. So by using satisfiability, it seems that we can synthesize programs. So this was the idea of synthesis via satisfiability. However, this idea that we can do synthesis via satisfiability is questionable. So let's go back to the print server specification. And remember, we had this specification, safety and liveness. And now we ask, is it satisfiable? The answer, yes, it is satisfiable. It is satisfiable in a degenerate model. There's only one state, and J1 hold and J2 hold. I'm sorry, J1 does not hold and J2 does not hold and P1 doesn't hold and P2 does not hold. So if you go back to the properties, where are they? Here are the properties. You see, they are always true because no job is ever submitted and no job is ever printed. So everything is true, but of course it's not very interesting. So why is it? What is the problem? We need to distinguish between input variable and output variables. And we want a program that handles all input sequences, all input traces, arbitrary input traces. So the reality is that we need to think that J1 and J2, which is submitted job, are input variable. They are controlled by the environment. The output variable are controlled by the system. So what we want is a system that handles all input sequences. And that satisfiability only give you one trace, and that's not good. We need all possible behaviors by the environment. So once we put aside satisfiability, we're going to back to this question. Now we're going to look at realizability. We mentioned realizability before. Now it's realizability over ongoing computation. So we have input variable I and output variable O. And now we can think of it, what's happening is a game between the system that chooses a truth assignment to the output variable, the environment that chooses a truth assignment to the input variable. So if both system and environment play, we get an infinite play because we assume no termination. Every state in the play is a pair of input assignment and output assignment. And what do we want? What does it mean to win? We have a formula phi over I and O. And we understand what it means for one behavior to satisfy the formula. But what we want is a strategy. The strategy is a function from all input histories to an output. And in 1989, apparently, Abadi, Lamport, and Wolper, Knoll and Rosner both said, look, what we need to check realizability, and we need to extract a strategy, a winning strategy. And the winning strategy is the program that we wanted to synthesize. Now, so this has to deal with all possible input sequences. So this is a universal plan. It's a plan that deals with all possible contingencies. Why do we want to deal with all possible contingencies? Well, think about it. You send something to deep space, something happens. The communication time back and forth is just too long. So you have to be ready for all contingencies. That's what we call autonomy. So a universal plan, all behaviors, all possible behavior by the environment. You dig a little bit and you find that this problem actually goes back to the 1950s. It was known for many, many years as Church's problem, because Alonzo Church posed the problem of realizability. He did not use temporal logic. He used monadic second order logic over one successor function. So it's MSO over one trace. This was the problem. It was posed by Church in 1957. 22 years later, it was solved by Bushi, and Landweber. They show that whether it's not realizable, it is realizable, is decidable. And not only that, if there is a winning strategy, it's a finite state winning strategy. So it's really synthesis. We get a finite state program. This was 1969. That paper is notoriously difficult to read. I don't know anyone has read that paper. But a few years later, 1972, Rabin came up with another approach, which could be understood via Rabin tree automata, and I'll get into it a little bit. But the interesting question here, so Church's problem seemed to have been solved in 1969, 1972. What the hell? Why do we give credit to that to Knoll and Rosner? What did Knoll and Rosner do? Because LTL we know can be expressed in monadic second order logic. In fact, LTL is first order logic. So the progress really, all the way going back to 1972, is better algorithms, better algorithms, better algorithms. So by now, we will be next year 50 years, 1972 will be 50 years of still searching for better algorithms. So what happened after 1972? So first of all, Michael Rabin said, okay, let's look at what is a strategy. So we said, we have a set of direction. Maybe a set of direction is just 0, 1. We'll give a binary tree. So the set of direction are the branches of the tree. The root of the tree is epsilon. And for every node in the tree, and a node is just going to be a sequence, a word over D, take xd for any other element D, that's the child. So really, the nodes of the tree are simply words over D, and we have the child relationship. And if you have a mapping from D star to sigma, that's a label infinite tree. Now, Rabin noticed that our notion of strategy, which is a mapping from 2 to the I star to 2 to the O, can be viewed as a strategy tree. So he said, let's forget about strategies, let's just reason about trees. And Rabin said, we're going to reason about infinite trees using finite set automata. So you're all familiar with automata over finite words. I will mention automata over infinite words, but we also have automata over infinite trees. There are finite automata over infinite trees. Now, the most fundamental problem for automata is the emptiness problem. Given an automaton, does it accept anything? So we will see in a few minutes, for example, the emptiness problem for DFA, which is very easy. What about the emptiness problem for automaton finite trees first? That was shown in 65 to be in polynomial time. In 69, Rabin introduced automata on infinite tree. Today we call them Rabin automata. That turned out to be a much more difficult problem. Rabin had an algorithm in 1969 which was non-elementary. So it's a tower of exponential whose height is unbounded. Hosel and Rakov were able to reduce it 3 years later to 2x time. Then Rabin reduced it to 1 exponential. Then in 85, Emerson and Stockmeyer and myself showed it's in NP. And finally, in 1991, Emerson and Jutla showed it was NP complete. So automata on finite trees, P time, automata on infinite trees, NP complete. So what is Rabin's approach? Rabin's approach for realizability of a formula phi was construct a tree automaton that accept all winning strategies. And it takes some creativity to construct such an automaton. But today, this is well understood how to construct this automaton. Then check non-emptiness of this automaton. And it turned out, if it's non-empty, the algorithm will give you, in fact, also a witness, which is the strategy. So we solved the problem. It's just non-elementary. Now, what's the source of non-elementary? Now, remember, in 1969, the algorithm, the non-emptiness algorithm was non-elementary. But in addition to convert from MSO specification to a tree automaton, was non-elementary. So this was inherently non-elementary. But in 1969, they had such fast computers, they didn't care about non-elementary. Now, what happened since? So first, remember, Rabin was still dealing with MSO. In 1977, Amir Pnoeli proposed LTL as the right specification language for ongoing computations. Okay. LTL you can convert to first order logic, which again has a non-elementary translation to automata. But in 83, Pierre Pernay showed that you have an exponential translation for automata. Now we think of typical exponential as bad, but this was a huge improvement because before that we have non-elementary. Now it's 1 exponential. This was for automata on words, and I'll come back to it. Then Safra showed how from this you get double exponential automata on trees. And Knoll and Rosner show how to check non-emptiness more efficiently. And when you put all of it together, we get realizability in double exponential time. And Pnoeli and Rosner was able to adapt a lower bound that Stockmeyer and I showed for CTL star. He was able to show this also applied to realizability. So now, by 1990, we understood the problem completely theoretically. It was 2x time complete. Okay, so a nice line of work starting from 1957. By 1990, we have a full theoretical understanding of the problem. So we thought. Now, you may think once we prove that this is 2x time, this is horrible complexity. There's no point in doing anything. We should just lie on the floor and cry. But I think this is too simplistic. Why? Because 2x time is a worst case complexity. And so, yes, there are indeed, you can write LTL formula, just that the smallest program that realizes them will be of double exponential size. So it's not clear that hand design would be any better. If you have such a problem, it's inherently difficult. So I wouldn't necessarily get all bent out of shape because of 2x time upper bound or lower bound. But the reality is the algorithmics are very, very challenging. And I'll get more deeply now, because remember, the progress has been much about algorithms. So I'll get deeper into algorithms. So what we have here is, first of all, we are using automata theory. So you're all familiar with deterministic automata on finite words. There are also deterministic automata on infinite words. They're called Bushy automata. I use NBW to denote that it's on words as opposed to trees. So inside the box, you see something that looks very similar. You have alphabet, finite set of set, initial set, transition function, accepting states. This is just like NFA. The difference is now we feed it an infinite input word. And therefore the run will be an infinite run. Just start from initial states and always choose a successor state. What is acceptance condition? Normally we said run to the very end and then check whether you accept or not. But here there is no end. So you have to accept infinitely often. And it turned out that this defined the class of omega regular languages, which is a very robust class with many very nice features. And it's equivalent to MSO. In fact, it's more expressive than LTL. But there is, let's look at two examples. So the first example is the word that contains infinitely many ones. You have alphabet 0, 1. I'm looking at all the words that contain infinitely many ones. So you enter, you have two set automaton. You enter on the left. 0 always take you to the left. 1 always take you to the right. The right circle are accepting states. So you see that to accept, you have to see infinitely many ones. Okay. Now the second one, the second example is slightly subtler. Now I want to see only finitely many zeros. So now I use non-determinism. You enter on the left, and you can stay on the left as long as you want. But if you stay on the left forever, you don't accept, because there's no red circle on the left. At some point, if you want to accept, you must go to an accepting states. You go to the right. But once you go to the right, you are only allowed to see 1. If you see 0, you get stuck, core dump, crash. So this automaton must see only finitely many zeros. From some point on, it must see 1. Okay, this is an important example. We'll see in a minute why this is a very important example. Now you say, why automata? I'm interested in linear temporal logic. Well, the key theorem is the compilation theorem. So think of temporal logic as a high-level language, and automata are low-level language, like assembly language, machine language. What Wolper and I showed in 1983, you can compile from LTL. LTL defined looks over infinite traces, and Bushy automata are over infinite traces. You can translate a formula into an equivalent automaton. It accepts exactly the traces that satisfy the formula, and the compilation is at most 1 exponential. So this is important because if you look at the history of logic and automata, all the translation before that were non-elementary. But LTL seemed to have the sweet spot between expressiveness and complexity. So there is exponential blow-up translating it to an automaton. Let's see again a couple of examples. If I say always eventually P, it means P has to be true infinitely often. And we just saw the automaton that does it. P takes you to the right, not P takes you to the left. And if I say eventually always P, it means there are only finitely many P bar, finitely many not P. And again, we saw the automaton that does it. You stay on the left, at some point you go to the right, and then you must stay on the circle state. Now we are going to do realizability games. Remember, we have a game here between system and environment. So what is the NBW game? The system chooses an output value. The environment chooses an input value. At every round, system and environment set their variables. We get an infinite word, an infinite play in sigma cos delta to the omega. And it has to be accepted by the automaton, which is over sigma cos delta. So this is an NBW game. You have an NBW that has a product alphabet, and we take turns. Vijay and I take turns on choosing. I choose one part of the alphabet, he chooses the other one, and we need the infinite word to be accepted by the automaton. Now we want to use it to do synthesis, and there we have a fundamental mismatch. Why? Because non-determinism, an non-deterministic automaton runs, you can think of it as if it sees the whole world and then it chooses the run because it had perfect non-determinism. So you can think of it as foresight. It looks at it started at the letter 0 and it sees the whole infinite world and then it makes the perfect choices. But in real life, we don't have it. When you have to make a decision, where do I go to school? This is the fundamental problem in life. All the big decisions in life, where to go to school, which profession to choose, which job to choose, which life partner to choose, all these very big decisions you have to make when you're young and naive. And you don't know what the future is going to be. So this is the difficulty. So how are we going to solve NBWs, NBW games? The answer is we must determinize the automata. But determinizing omega automata seems to be difficult. And this, again, goes back to 1961 Landweber. He showed that for Bushy automata, non-deterministic automata are more expressive than deterministic automata. Remember, in 1959, Rabin and Scott showed over finite words, non-determinism does not add expressive power. It's succinctness, but not expressive power. This is an important result. It's part of the, for the introduction to non-determinism is partly what they got the Turing Award. Non-deterministic automata are more powerful. And the example is exactly the example of finitely many zeros. Because at some point I have to choose I have to go to the red state, but how do I know when to go? So we didn't know how to determinize automata. Finally, in 1966, McNaughton showed how to determinize automata. I won't go into detail, but his construction was doubly exponential. Now, what you need is, you can do with Bushy automata, you need more general acceptance condition. And there was lots of people studied different acceptance condition. And finally, in the 80s, we converged on somewhat strange acceptance condition, and it's called the parity condition. What is the parity condition? You have a partition F1 to Fk of the state space S. K is called the parity index. Now, because it's a partition, one Fi must be visited in infinite run. One Fi must be visited infinitely often. And you want the least I such that Fi visited infinitely often to be even. When you first see it, you think you scratch your head. All I can say is you had to be there. This emerged as a very robust notion of acceptance that has many advantages over other notions of acceptance. In 1988, Safra shows you can start with a Bushy automaton with n state and end up with a deterministic parity automaton with n to the big O of n. But importantly, the number of sets in the partition is linear. So you have large exponential state space, and not just exponential, but not a very friendly exponential. It's 2 to the n log n, not 2 to the n, 2 to the n log n, but a small parity index, a linear parity index. Now, corresponding to parity automata, we have parity games. What are parity games? You have a game graph where you have two sets, V0 and V1. V0 player 0 makes a move, V1 player 1 makes a move. And they make moves. They start in one node, they go from V1 to 0 to V1, from V1 to V0. Again, the winning condition is a partition. And again, player 0 wins if the least I, such as WI is accepted visited infinitely often, is even, kind of a matching condition. So these are parity games. And the complexity was open for many years. And finally, in 2017, Kalud et al. Showed that the complexity is in quasi-polynomial time. What is quasi-polynomial time? It is 2 to the polylog. It's still an open question whether it's in polynomial time. This is still major open question. But at least we know how to solve parity game, at least in quasi-polynomial time. So this is today how we can do LTL synthesis. We start from LTL formula phi. We convert with one exponential blow-up to non-deterministic Bushy automaton. We convert with another exponential blow-up to deterministic parity automaton. And then we solve the parity game in quasi-polynomial time. When you put it all together, it's in double exponential time. and you can extract a program, a transducer, which we will see the precise definition in a few minutes, with double exponentially many states. So we have a solution. Again, theoretically, we understand it. Now, you might think that logic and automata are somehow inherently something does not lend itself to practice, but they have many success stories. For example, Mona is a package deal with automata with monadic order logic on finite words. And it's non-elementary, but actually in many cases it works well. Yes, some cases it will blow up, but many cases are successful. In fact, I will show you later how we used Mona. Automata theoretic model checking is an industrial success story. Even, there are lots of works on people using automata for decision procedures. But this one, elegant theory, very, very difficult to reduce it to practice. So why is it so difficult? The answer is determination. There are two steps here that are very difficult. One is determinization is very difficult. Big difference between 2 to the n and n to the n. Okay, take a n equal 20. 2 to the n is just a million. N to the n, humongous number. Okay. Now, also the state space of deterministic automata is rather complicated, and it means it's very hard to apply the symbolic algorithms. In parity games, we saw it's still quasi-polynomial time, they are hard. There have been very good recent progress recently, just last year, there was recent progress about better translation. In fact, you don't have to determinize, you go directly from L to deterministic omega automata, but it is still hard. So work in progress. So one solution was people say, you know what, let's use less expressive. Don't use full LTL. We'll use something less expressive. What do we use? It's called GR1, general reactivity 1. And basically they say we're just going to reason about fairness conditions. So we have something like always eventually P implies always eventually Q. That's an example of GR1. Okay. You have essentially one such implication. It's slightly more general, but I won't go into the precise definition. So Peter Magnoli and Saar showed that the GR1 game is easier to solve than parity game, and tools have been built. And this has many applications, especially in robotic. People are using this. But the main weakness is the expressiveness is very low. Okay, you're only dealing with fairness. You cannot, there are many, many things you cannot say in this logic. So in 2013, Giuseppe De Giacomo and I proposed a new approach. We said, why, the source of the problem is this, there's this beautiful theory of automata on infinite words. Let's consider LTL over finite words. Now, remember, the motivation for infinite traces was non-terminating programs. But our observation was that there are many, many applications where we are interested in temporal reasoning, but we want termination. So why do we want termination? AI planning, robot task planning, business processes. So what happens if you have a finite trace? And for example, you have always eventually P, means P will be true at the final set of the trace. And in fact, there is a logic people have called co-safe LTL. And it's very popular because there are lots of applications where people do want finite trace LTL. So when you go to LTLF, we call it LTL over finite traces. It is also 2x time complete, but the algorithmics is much easier. So I'm going to dive into the easier algorithmics. So for this, first, let's look at what I call classical AI planning. Classical AI planning is really reachability over deterministic finite automata. So again, you have an alphabet set of states, initial state, transition function, accepting states. And the planning problem is just find a word that is accepted. So usually if you take course in AI, you read about strips planning, and it's not described as DFA, but this is what it is. You have a finite domain, you have action, the action have deterministic outcome, and you need to find a sequence of action that will take you from initial to goal state. And this is an easy algorithm. This can be done in linear time, in n-log space. This is an easy problem. And what is the program? Non-realizability just means that the automaton is non-empty. And the program is this sequence of action, the word There is a word that takes you from initial to accepting state. This is classical AI planning. Now we want to think, however, of in this classical planning, there's no environment. It's all about, there's no adversarial aspect to it. We're interested in adversarial settings when the environment could be adversarial. So let's, instead of reachability, first let's talk about reachability games. So reachability game, we have again a game graph, and the nodes V0 and V1 of player 0 and player 1, but they take turns moving the nodes. So if you're at V0, player 0 move. If you're at V1, player 1 move. And the goal of player 0 is to reach the winning state, and the goal of player 1 is to stop player 0 from reaching the goal state. And we know how to solve these games in linear time. I will just say something you can check later. It's really essentially Hoare and SAT. And Hoare and SAT today, you give it to a SAT solver, it's just Boolean constant propagation. It will be solved blazingly fast. Okay, blazingly fast. Now we are interested in what is called in our universal planning, where you have to consider adversarial environment. So I'm going to take the DFA game, and again I'm going to the same idea. The alphabet is a product alphabet, and the system control one part of the alphabet, environment control the other part of the alphabet. So we take turns, the system and the environment take turns choosing the component of the alphabet, and eventually you get a finite trace that should be accepted by the automaton. So again, what we want is there a winning strategy, and we want to obtain such a strategy. So this is also, we can solve it fairly easily. And here is the easiest way to think how to solve it is to do backward induction. Let's compute the set of winning state. So if you're in accepting state, you win immediately because you're already accepting states. Once you compute the win sub I would say win sub I plus 1 will be everything that you win in I moves, plus all the states S, such that there is a letter A, you can choose a letter A in sigma, such that for all B in delta, the transition from S when it read AB is into a state that you win in I moves. So this is classical backward induction. This is like if you have a finite game tree, you label the nodes, and then it's an and or tree, you work your way and you label all the way to the top. And again, we can do it in linear time. So this is realizability, we can do linear time. The program we want to extract are transducer, or some people call them Moore machines. And the only difference between this and automata is also we have, instead of acceptance, we have an output function. We have a function that for every state issues an output. So here you have the deltas are the input actions, and the sigmas are the output actions by the system. Now, notice here that when I do this fixed point, not only I choose the set S, but I choose the letter A, which is the good move for the system. So all I have to do is keep track for each S, keep track of that letter A that wins against all letters B. And this is how you define the transducer. Essentially, you get a transducer by pruning the DFA and only keeping the winning moves. Now, this is the theory, and that theory was developed first by Di Giacomo and I, and the observation was you have an LTLF formula, you can translate it to DFA, and then you can solve the game DFA. A few years later, with a bunch of other people, Juta, Bahara, Lee, and Poo, we actually reduce it to practice. We use Mona to build automata. We translated the LTLF to first order logic. We use Mona to obtain from this symbolic DFA. And the advantage of having symbolic DFA that we can solve the game, you can implement this fixed point algorithm symbolically. And we have a tool that you can find, it's called SIFT. And when you compare, you can reduce LTLF synthesis to LTL synthesis. So we did a comparison of SIFT against, this was at the time, the best tool available at the time. And as we increase the size of the formula, Acacia Plus declined very quickly, and you can see that SIFT has managed to scale up much nicer, okay? So by doing dedicated techniques built on DFA, we're able to perform much better than LTL synthesis tool. So let's have a little discussion. LTLF synthesis, it's still 2x time complete. Okay, we have not changed that. But as I mentioned, the worst case analysis is pessimistic. And in fact, much of the research we're doing today, we're building hugely successful SAT solver. We talk about the SAT revolution. When I go back, when I was a graduate student, people say NP complete is scary. You don't touch it with a 10-foot pole. Model checkers solve space complete problems. What we need are algorithms that can blow up only on hard instances. And so you need more, so overall, we need more algorithmic research. But the question I want to ask is, okay, can we use DFA technology? So we see that using DFA makes it easier for us to build algorithms. Can we use DFA technology beyond LTLF? We show how we can use it for LTLF. Can we use it beyond LTLF? And the way we do it is we go to full LTL, but we limit full LTL. And we focus here on what we call safety LTL properties. And what is safety LTL? We said, don't have full liveness. Take away until and take away eventually. You can have always, you can have next, you can have weak until. You can have release, but no until or eventually. So for example, if I said before, always send implies eventually receive, that's the thing that makes it very difficult. Instead of saying eventually receive, you must decide on a time bound. You can say always send implies next receive. So now I've taken away the eventualities. Now it is safety LTL. And we are going to have, again, linear game solvability, and there is a tool, safety sift. And again, what are the algorithmic ideas here? If phi is a safety formula, not phi is a cost safety formula. In cost safety formula, the feature is, if phi is a safety formula, a counterexample is always going to be a finite prefix. So we can translate it from not phi to DFA, and now we'll have to solve for the adversary of the DFA game. And again, now we can translate not phi to first order logic, use MONA to BDD, symbolic DFA, and solve DFA game symbolically. The key was that we're solving first for the adversary. And again, we benchmark SIFT against LTL synthesis tool, Acacia Plus, Horensat, and Beast. And you can see that SIFT scales up much better than LTL tools. So again, we see, and we're building it on DFA technology. So now we're kind of greedy. We want to see, can we get the best of all possible worlds? And we saw two success stories, GR1 and finite horizon synthesis. Is it possible to combine them? Now, first you may ask, why would we want to combine? If you only care about finite horizon, why do you care about GR1? And the answer is, even if your goal is a finite horizon goal, the assumption may need to be infinite horizon assumptions. For example, if I want if the property is eventually received, to make it happen, require, for example, that infinitely many times the channel will be up. So how do we combine GR1 with LTLF? We use GR1 assumptions and LTLF goals. And in ICHKAI 21 paper, we show that we can use, again, DFA technology. We construct deterministic automaton. On deterministic automaton, we will have to solve GR1 games. So we use DFA to construct the arena, and then we use the GR1 game to solve the game. And again, we show that this outperform LTL synthesis tools. So let me conclude. You may have heard me some years ago talk about the siren song of temporal synthesis. And the siren are mythical Greek mythology. They're mythical creatures. They are on an island. They sing very, very beautifully. And if you hear the song, then you never want to leave. And then people get stuck there. So LTL synthesis is a beautifully seductive idea. But we saw that you have very challenging complexity and very difficult algorithmics. So we use infinite horizon semantics, and it's expressive, but we pay a very high price, which is painful because I kind of built my career to a large extent by developing the theory of omega automata, or automata on infinite worlds, automata on infinite trees. And now I said, you know what? We have to go back to finite horizon automata. And I think the philosophy is what I call life wisdom. You can run farther by running slower. So let's have a compromise. Let's focus only about properties about finite horizon, and they're less expressive, but we have much better algorithmics. And I think it remains to be seen, how much of the classical temporal synthesis we need to abandon, and how much of it can we move to based on DFA technology instead of like a deterministic parity automata and parity game. So the theory will be beautiful, but maybe there is a debate also, like in physics. Does beauty imply truth? And very often mathematicians and physicists say beautiful, it must be true. But there are some criticism. For example, in string theory, it's very beautiful, but people say the physicists have been seduced by beauty. So here, I spent decades of my life studying this omega automata. I still publish paper to this very day about omega automata, but maybe we've been seduced by beauty. Maybe you need to be more modest and investigate more finite horizon temporal logic. Thank you very much.
Thank you, Moshe, for a wonderful talk. Let me clap for everybody here. So questions, are there questions? I think, Jay, can you allow for it to be, allow the participants to unmute themselves?
Yeah, I think they can unmute themselves anytime they like.
Yeah.
I see that Stefan has a question.
Yeah, Stefan, please go ahead. Well, Stefan was also clapping, but yeah, go ahead.
Unmute and show your face. I want to see what you look like. Thank you.
We can't hear you, Stefan.
Put your question in the chat. In the meantime, anybody else?
So while people are, Rajiv wants to ask a question. Go ahead, Rajiv.
Hey, Moshe, how are you?
Hey.
Let me turn on my video so you can actually see me. There we are.
Yeah. I have to say something. Good day.
Fair enough. This finite trace business that you talked about, isn't that just bounded model checking?
No. Bounded model checking goes one step further. Bounded model checking says we're going not to go to do finite traces, we're going to do bounded traces. We decide, okay, we're going to look for bugs up to depth 100, depth 1000, okay? We are still doing finite trace. We don't put a bound on the on the length of the trace, okay? Now in practice, the bound will come from the bound is going to be double exponential bound, because the game of double exponential size. So if there is a winning strategy, I compute this fixed point. So the fixed point must converge in double exponentially many steps. So the longest before, if you have a winning strategy, at most you'll have to play double exponentially long. But a priori, I'm not making this. It will fall out of the solution rather than an assumption. Bounded model checking but bounded model checking has kind of the same philosophy, which is you can run longer if you run slower, okay? If you run a marathon, you don't do it in 100 meter per 10 seconds, right? You run slower. So the same idea was model checking was difficult. Can we instead make it easier to say, okay, most bugs are shallow. There was a philosophy, most bugs are shallow. Let's try to find bugs up to a fixed length. So it's even more extreme. And there is some discussion, there is some study about something called bounded synthesis, but it's not exactly the same. It's not about the length of the game. It's more about, you make assumption about the size of the strategies, either of the system or the environment. But all of them have the same philosophy. It's a difficult problem. Let's just be a bit more, let's lower our aims and do more. And I think that's generally is a kind of good principle inside. You're trying to solve a difficult problem. You're not being successful. Try to solve an easier problem. Part of the hope is sometimes by solving an easier problem, you develop technique that might enable you then to go back and attack the harder problem. So This is the approach here. So I love the picture of Guantin Pond.
Yeah, Tony, he's one of my students. Please ask a question.
Oh,
Yeah. Hi.
he has a doggy. He has a doggy picture there. I love dogs. It's okay.
Yeah. Yeah.
So I have many questions, Moshe, while others are thinking about questions.
Yep.
There is this general trend we are seeing in verification, right? So we are, you talked about bounded model checking. Here you talked about finite traces using DFA technology. And there seems to be a gap between theory and practice in general, if you will, right? Complexity theory says the problem is NP complete or P space complete, or doubly exponential for that matter. And yet there are many, many problems you can solve in real life. And so it has to be the case that there must be some structure, or at least one conjecture is there must be some structure that's being exploited. And so there is this gap between theory and practice. And do you have any thoughts about how this gap can be addressed in a general sense?
So when I was a freshman, and I thought that PhD students are infinitely wise, and my PhD TA asked us, what's the difference between theory and practice? And we looked at each other, man, we didn't have a good answer. And he said, in theory, they're not very different, but in practice, they're very different.
Right.
So I think that for computer science, the gap between theory and practice is a huge challenge.
Yeah.
And I think I view it as, if you go to, I mean, you kind of see it also in physics where the string theories just go their way. And I think somebody's written a book called Not Even Wrong. So this was a term due to Wolfgang Pauli, not even wrong about this, because it's just not clear that this is, or take the other theory, they have multiverse theory. It's just not clear at all that this is experimentally verifiable or falsifiable. And this interplay between theory and physics, the way when I was an undergraduate student, my major was physics. And there's this interplay between theory and experiment, not practice, but it's experiment, where, yeah, the theorists can come up with beautiful theories, but at the end of the day, there are lots of theories in physics. I mean, huge number of theories, but at the end of the day, does it stand the test of experiment? And the huge success, sometimes we had amazing, like just this week, I read something in the paper, general relativity has been confirmed once more, some other experiment, okay? Which is amazing. Somebody has a theory and it actually, you do the experiment and they are very verifiable, okay? Now, somehow in computer science, in certain areas of computer science, people have kind of abandoned that idea that we have to have a theory that would somehow match also the experiment part. I'm not saying that every paper should have theory and experiment, but to me, complexity theory, when kind of, what is the goal of complexity theory? Is ultimately, when you look at the root, was to explain some problems are hard, some problems are easy. Can we understand why? Are the problems, are they inherently hard or not hard? And somehow, very often the theoreticians are pretty happy with just asking the theoretical question without, it's not that they're not doing the experiment themselves. The fact that there is no interplay between the theory and experiment complexity theory bothers me, okay? There are some exceptions, we've just, we played a role in publishing a chapter in a handbook beyond worst case complexity.
Yeah.
But I think it's an exception rather than the rule, and the editor of that book, Tim Ravgarner, is one of the more enlightened theoreticians who understand that there is a bit of a problem here.
Right.
And the answer is, do we need better understanding of the practical problems, which is one line of work? Do we need to different definition, revisit basic definition? In what Tim Ravgarner is trying to do is to revisit the basic definition in complexity theory.
Right.
We took worst case complexity for two reasons. One is mathematically more amenable.
Yes. And
the second thing is, you can say, look, if I give you a worst case upper bound, and it's good, you should be very happy.
Right.
But suppose now we're facing the following. Suppose I give you one algorithm is quadratic, and the other one is exponential. I ask students this question, which algorithm is better? They say quadratic is for sure better. I tell them, but the quadratic is always quadratic, and the exponential is always exponential on a very, very small fraction of the problem. And it's linear on all the other problems. So which one in practice do you want to use? I say most of the time, run the exponential algorithm. If it runs too long, then you switch to the quadratic algorithm. That's really what you want to do. We don't even teach that to students. I think go to the person who teach algorithms. Ask, do the graduates from Waterloo, do the graduates from Rice? I don't teach the algorithm course. Do the graduates from Rice University, let's not pick on someone else, my own institution, do they realize that this is a very coarse measure of worst-case complexity, right, and it hides a whole bunch of stuff? Now, if you prove even if you prove a lower bound, what does it mean? It means there are some hard instances. That's what it means. It doesn't mean all instances are hard.
Right.
So I think as a discipline, we have a major issue.
Yeah, and there are some efforts like parameterized complexity or smoothed analysis, and there are some efforts in. And I think I recall you mentioning one idea where the exponent is not very 2 raised to cn, but c is very small.
If c is very small, Yeah. So I'll give you an example. I was student do the master thesis on computing the permanent.
Mm-hmm.
Okay, so computing the permanent has a FP-RAS, fully polynomial randomized approximation scheme. Okay, the polynomial is like n to the 11. The constants are huge, and he implemented an algorithm, an exact algorithm called Reiser's algorithm, and he showed that because the exponent is relatively, constants are small, that algorithm it's going to be better than the polynomial time algorithm up to n, which is large enough. And by the time you get to that n, the n to the 11 is completely impractical.
Right. So
this FP-RAS algorithm, which is a beautiful theoretical result, is completely useless if you really want to compute the permanent. And our application, this is the problem with applications. So it's a beautiful, useless result. By the time your algorithm is better, difficult to implement.
Yeah.
And by the time it's better than the exact algorithm, the universe is all of the entropy has gone down to 0. So not going to be very interesting.
Yeah.
But again, you go to the theory community, and this just understanding this and talking about it, it's just not there.
Yeah.
I had a student that kind of got a theoretical result and was a theoretician. I brought him to Rice, brought him to formal methods. Then he wanted to go to a conference first summer. I said, would you send me to a conference without a paper? I said, okay, one conference I'll send you without a paper. I think you should go to CAV. So, oh, I really, really would like to go to Stock. I've never been to Stock. I really, really want to go to Stock. So I said, okay, I'll pay you to go to Stock. He come back from Stock after he was a year at Rice, and I've already corrupted him. He come back from Stock. I said, what did you learn? He said, I learned I'm not a Stock person.
Yeah. No, they have a very particular standard for what they consider a good result. So another question.
The story is about, we mentioned one of my students before, and now we have a public, so I don't want to mention his name. He has done some work where there is elegant theory and also run experiments. Right. And he thought, this is a classical problem coming from the theory community, approximate counting. I'll send a paper to Stock. He wanted to have a paper at Stock. And he thought, I have theorem and experiment. People saw the paper, they say, you have experiment. What are you doing here? They rejected the paper because he had experiments.
No, I concur with you 100%. This gap between theory and practice is the biggest problem. And that's why, we are trying to get some theorists interested in the SAT problem, like why is SAT efficient and so on.
Yeah.
So that, I segue to SAT, and you mentioned using SAT to solve the problem, and you showed the graph where Horn-SAT was able to solve, but your specialized algorithm did much better.
Horn-SAT was pretty good because it's incredible. You just take SAT solver, any SAT solver. Right. All they have to do is BCP, so it's very, very fast. But the problem is that we generate, the encoding is such that the problem become very large. So even though it become Horn-SAT. because we have BDDs, and with HOR and SAT we have to basically write down all paths in the BDD, and that's what the blow up comes out. So we lose the BDDs are very good at representing sparse spaces, and we lose it when we went to HOR and SAT.
So there is
it doesn't mean we should give up on trying to use SAT technology for this.
Well, one way I was thinking was you could extend the BCP with specialized routines, just like SMT. SMT takes a SAT solver and you extends it with theory. If you could extend it with a theory solver for LTL over finite traces in some sense, then perhaps you would get a much better, it would be a combination, but a much better method than what you have now. That's possible.
I've hopefully you have understood from this talk that I view this as what is the phrase from Casablanca? This is the beginning of a beautiful relationship. I'm hoping that this will inspire people. I think there is a lot of room for improvement. I mean, one of the things that we have learned, I think, from SAT and similar and model checking, formal method community have shown is the importance of algorithmic engineering. Okay.
Exactly.
That when you have a whole community bidding on a problem, and really with algorithmic engineering, more and more clever, you have lots of people that throw wet paper on the wall to see what sticks. And over the years, this phenomenon called Moore laws for SAT solver shows the power. What happens when you have a whole community saying, we're going to bid on this problem, and not necessarily by great theoretical advances, by very, very clever algorithmic ideas. This to me is a amazing success what happened in SAT. I really think that there are two things. One is that we can do so well on an NP-complete problem, but just what happened when enough people just get obsessed. We're all suffering from OCD. When enough people get obsessed with a problem and they bid on it day and night, how much progress we can make is amazing.
I had another technical question. So there was one slide where you mentioned that non-deterministic Bookey automata and the expressive power, it's much more expressive than deterministic. There exist languages that you can accept using non-deterministic Bookey, but not using deterministic Bookey. So within that context, but then you mentioned that there is a way to determinize it, but you still don't get the expressive power when you do the determinization, right?
No, you can. Yeah, you get the full expressive power, but you need to use more general acceptance condition, like parity condition. So the full, there is a condition we call omega regular, which is non-deterministic automata, non-deterministic Bush automata, NBW define omega regular languages.
Right.
The deterministic parity automata have the same expressive power.
Okay.
But deterministic Bush automata do not. So Bushy condition was actually, turns out, nice condition, beautiful theory, but it's too weak to capture. If you want determinism, you need a more powerful acceptance condition.
Sounds good. And are there additional questions, by the way? If not, thank you, Moshe, for a wonderful talk. And the next session for the conference will start in about 20 minutes or so. So thank you again, and really enjoyed the talk. Thank you so much.
Thank you all, and have a good day, good evening. Some people are probably in the middle of the night, so.
Right.
I think we need to say, instead of saying, usually we say good, like good something. I think we need to say good time. Have a good time.
Yes.
Okay.
Awesome.
Bye-bye, everyone.
Thank
you
you
again for the invitation.
Bye-bye. Thanks.
Hello.
Hi, Robin. Could you please put up your slides now? Because is it about 2 minutes to go, according to me?
Yep. This should work.
Yeah, I can see it.
Perfect.
Now, Robin, your talk goes for 25 minutes. Would you like me to give you a reminder or something like that at the 15-minute mark?
No, I'm fine.
You're fine?
Thank you.
Okay. All right. So what I will do, though, is I'll give you a warning at the 5-minute mark.
Yeah.
Is that okay?
That's
right?
Good. Thank you.
Yeah. So what I'll do is literally I'll just unmute my microphone for a second and say 5 minutes, Robin, or something like that, right? And if you could acknowledge that, then I can just switch my microphone off again. Yeah.
Yeah, we will do that.
Okay, great. So where are we? Oh, I've lost my. Okay, according to me, it's about time to start. Is that okay with everybody? All right. So, hello everybody. Welcome to the next section of ATVA. Our first speaker is Robin Ziemek from TU Dresden, and he's going to tell us a little bit about probabilistic causes in Markov chains. All yours, Robin.
All right, so yeah, I'm gonna talk about our paper, Probabilistic Causes in Markov Chains. This is joint work with Christel Bayer, Florian Funke, Simon Jansch, and Jakob Biribauer, and we're all from Technische Universität Dresden. And in our paper, we have two main things going on. The first one being monitoring. Monitoring is we observe a system at runtime, and the monitor then checks whether the system at runtime behaves according to a given specification. And it also can raise an alarm whenever critical events occur or are likely to occur. And the other thing is already in the title, it's causality. Causality in itself is a philosophical concept that we meet in our everyday life. But in the philosophical theory of causality, there are a lot of principles, and we picked two main principles we use for our notion of causality. The first one being non-probabilistic counterfactual reasoning, which basically says that an effect cannot occur without a cause, or the counterfactual idea is the effect would not have happened if the cause would not have happened. And the other idea we use is probability raising. Probability raising just says that whenever a cause occurs, it raises the probability of the effect to happen. And now we have these two concepts, monitoring and causality, and our goal is to develop foundations of causality-based monitoring, especially in a probabilistic operational model, namely Markov chains, like in the title. My talk right now will be structured that I start with briefly introducing Markov chains as a probabilistic model. Then I will define our notion of causality within Markov chains, give some motivation for monitoring purposes, how it can be used there, and show some properties of these causes. And then going back to monitoring, we try to compute optimal causes with respect to different situations. Therefore, we defined cost functions, and then we had some complexity results on how to compute optimal p causes. And in the end, I will conclude the talk. All right, so Markov chains. A Markov chain is basically like depicted here in the picture. We just have a finite set of states. Here, these are 5 states. These states have a unique initial state within them, where we start with every execution in the system. And then we have transition probabilities outgoing from every state to go to another state, and the outgoing edges always sum up to 1. Yeah, so this is a Markov chain, and now we want to define a causal structure within there. And for this, we of course first need to think about the effect before we think about the cause. And with the monitoring in mind, we think of the effect as some critical event that we should not occur, and therefore we think of a set of states that we want to avoid, and then the effect is the event that we reach this set of states. And we also fix a probability threshold that should be greater or equal than the initial probability to reach this effect set. And then we start incorporating the probability raising principle by defining our first thing, p-critical prefixes, which are just finite paths for which the conditional probability after observing such a finite path to reach the effect state or effect set is greater or equal than p. And then if we put these two inequalities together, we see that this is a non-strict probability raising property. This also yields a set of acceptable final states for these p-critical prefixes. These are just states from which the probability to reach E is greater or equal than P. This we can see easily in an example. It's the same Markov chain as before. Now, error is our effect set, and the probability threshold is 3/4. And then we see that the states T and U are acceptable final states for these p-critical prefixes. And for example, then the finite path S0U is a p-critical prefix. Note here, the name critical comes also from the motivation of monitoring, since we are kind of probabilistic critical whenever we are observed such a path. All right, this was the first principle. To talk about the counterfactual idea, I first define our notion of causality in full. It's the notion of a p-cause, p still being the probability threshold as before. And then we say a p-cause for eventually reaching the effect set is a prefix-free set of finite paths, such that on one hand, almost every path that reaches E has a finite prefix in there. And on the other hand, each of these finite paths in the p-cause is a p-critical prefix. And now we can see in the first bullet point that this is actually counterfactual reasoning, because we cannot observe the effect, eventually E, without seeing a path in the p-cause. And therefore we have these two principles in our definition. Again, as an example, we can look at the same Markov chain as before. Also, the effect set is error and the same probability threshold. Like I said before, S0U would be a p-critical prefix, but to be a p-cause, we now need to have this property that almost every path reaching error has a prefix in there. And in this example, it suffices to take S0T as another path in there, and then every path actually that reaches error has one of these two paths, finite paths, as a prefix. All right. So now the question would be how can we use this, or is it useful in applications? And there the counterfactual idea comes in. Since almost every execution exhibiting the event of reaching E now has a finite prefix contained in the p-cause, we can use p-causes to monitor a system at runtime. To see this, we look at another example. Now, this is another Markov chain. Here I omitted the transition probabilities. The only interesting thing is that S1, S3, and S4 are acceptable final states for our p-critical prefixes. And we think now of error, hence the name, as a critical event that the system should avoid. And if we now know a p-cause for this structure, let's say S0, S1 as one path and S0, S2, S4 as another one, then we can build a monitor from there that raises an alarm whenever the execution so far is part of this p-cause. And therefore we can take suitable countermeasures according to how critical the alarm would be. So some properties of our p-causes are that they are not only applicable for reachability properties, like when we have a set of states and we say the effect is reaching the states or the set of states, we can also reduce the effect to be an omega regular language. To see this, we just consider any omega regular language over the alphabet of the state space of the Markov chain. And as it's known, every omega regular language has a deterministic automaton accepting that language. And with this automaton, we can now compose the product Markov chain. And like in every Markov chain, the paths in there eventually end in a bottom strongly connected component, which they cannot leave anymore. But since the property is omega regular, these BSCCs can be accepting or rejecting, resulting in the corresponding path in the former Markov chain, satisfying these conditional probabilities here. Since these paths end in such a BSCC in finitely many steps, this means we can, for almost every infinite path fulfilling the omega regular language, we can find a finite one critical prefix, which is just the corresponding path in the BSCC. And this also leads us to being able to compose p-causes for any p, since we have the inequality and one critical prefixes are the best we can hope for. On the other hand, if we now think of the union of all accepting BSCCs, the product Markov chain, we get the equality that for all finite paths, the probability to fulfill L after seeing the path is equal to reaching any accepted BSCC in the augmented path of the product Markov chain. And therefore, it actually suffices to focus on reachability properties, and we still have this case of omega regular languages covered with our approach. Like I said right now, we have also the property that p-causes always exist for any p. And there's one particular one that we can motivate through a different idea, that one being defining a partial order on the set of p-causes. We say a p-cos pi is less or equal than a p-cos phi if for every path in phi there is a prefix in pi. So for every path in here we have a prefix in here. This actually is a partial order. This comes crucially needs the prefix freeness that I had in the definition before. This is a little technical thing. And if we now recall from the definition of p-critical prefixes that we have this set of acceptable final states, then we can also see that this partial order admits a minimal regular element, namely it's just a set of paths that end in such a acceptable final state. So the last state of these paths is an SP, but it does not visit this set with any prior state, and therefore it's accepting with the first possible moment, so to speak. And this cause is then called the canonical p-cause. This is actually interesting for the complexity results for the applications later on, since this regular element can be computed pretty easily and also is pretty easy as seen as a finite monitor. So speaking of cost functions, now going back to the monitoring application, we have in the motivation I said that the p-cause is given. And this, of course, depends on the p-cause, if it's suited or not to the situation. So the p-cause should be computed before the system is put to use, but it's not clear which p-cause would be optimal depending on the situation. And to tackle the question which p-cause we should choose, we had the idea to incur cost functions on the Markov chain. So the idea here is that any cyber-physical system consumes resources of some kinds, and they normally come with budget restrictions. And even on on another side, the countermeasures we take upon raising an alarm may also incur costs, which could depend on the state of the system or the execution seen so far. And we model these costs in the Markov chain as just state weights on the state space of the Markov chain. So every state has a corresponding weight. And then these state weights induce a cost function on finite executions of the system by either accumulating the cost along the execution, which is practical if the costs depend on the execution so far, or we can also have a cost function in an instantaneous fashion, which just takes the cost of the last visited state, which makes sense if the costs depend on the state of the system. Now, obviously, this does not suffice to define in which situation which p costs should be computed and how to compute them. We still need further definitions of cost variance. And to motivate them, let's look at different situations. Right here, we have the Markov chain as before, omitted the transition probabilities here, but now we have weights on these states. Here the weight is 0, and I didn't write it down therefore, and here we have these weights given. And for our first situation, let's think about what happens if the weight function models cost of monitoring the states themselves, and we actually want to optimize the cost of the monitor. Then, of course, we need to incorporate every execution that can happen, and therefore we need to have an expectation of all accumulated costs in every scenario, which, since we have an expectation here, depends on the transition probabilities. So it's not clear if a p-critical prefix in our p-cost should stop at S1, or if it should go through to S4 and S3, depending on the transition probabilities here. Note that the execution to save will always be in there, since we have to look at all scenarios in this case. And we defined exactly this kind of cost variant. And in this situation, we would then want to find a minimal cost for these expected costs, like we defined in our paper. Another situation would be if the costs would be modeled as the cost of countermeasures we take. Let's take, for instance, if these costs depend on the current system state, which makes sense for countermeasures. And we would then want to optimize the cost of an alarm. This is a different situation, since right now we don't need to take into account every execution of the system, but only the executions that actually raise an alarm, which means that we have a partial expectation, since we only take the accumulated or the instantaneous cost if the cost is reached, and not in other cases. And for example, for the instantaneous weight function or for the instantaneous cost function here, it is clear that we should not stop at S1 for our pre-critical prefix, but should go through to S3 and S4. And we defined partial expected costs also in our paper. It does pretty much the same as I explained here, and then we want to find a minimal cost for these partial expected costs. And a last situation that I want to motivate here is if the weight function models any cost that has a tight budget restriction, and we have to make sure that our system does not go over this budget restrictions, which makes sense if this is some kind of energy or current energy consumption or something like this. And then we want to optimize for the lowest possible cost, which does not depend on the transition probabilities anymore, since we then take the maximal cost of any path in the course, which is not dependent on the transition probabilities anymore. And therefore, of course, in this example, if we accumulate the cost, it makes sense to stop at S1 and not go further, since we would accumulate more costs and the transition probabilities don't change anything. So we want to find, in this case, a minimal cost for the maximal cost. And for these three cost variants, we have complexity results and how to compute minimal p causes.
Sorry, Robin, 5 minutes.
Yep. Yep. All right. Thank you. And yes, so this is basically our complexity table, so to speak. We have these three cost variants here. We have different situations where we have non-negative weights and accumulate, or we have arbitrary weights, accumulated or instantaneous. And here's the complexity on how to compute optimal p-cause. Note here that for the expected cost and maximal cost for non-negative weights, the canonical p-cause is actually optimal, and therefore this computation is pretty easy. This is not the case in the other p time algorithms. And the pseudo polynomial algorithm for the partial expected cost comes from a reduction to partial expectations in MDPs. And for maximal cost, it comes from a reduction to game theory. So this is also different. And also the lower bound of PP hardness here, which is a complexity class defined by a probabilistic polynomial time machine, Turing machine, not to be confused with pseudo polynomial, comes also from this kind of same idea, a reduction to an MDP structure, but we do not have a lower bound, an upper bound, sorry, for the partial expected cost in the arbitrary weight case, which comes from the fact that our reduction to the MDP structure actually yields Golem hardness in the arbitrary weight case, even when our MDP structure is pretty easy, it does not suggest why this should help for the computation. So yeah, these are the complexity results. And now if I try to conclude what we did in our paper, I would just briefly say that we used these two principles, counterfactual reasoning and probability raising of causality, to combine them in a notion of causality in finite Markov chains. And then we motivated that we can use these p-causes in monitoring applications and defined cost mechanisms to help finding suitable causes for these monitoring purposes. And the question now would be, where can we go from here? One idea would be on the theoretical side to define causes in Markov decision processes, which are a generalization of Markov chains with non-determinism. And on the other side, on the monitoring side, it would make sense to consider monitors with imperfect information, which is not done here, by extending our framework to hidden Markov chains. So this would be future work that should be tackled. All right, then I thank you for your attention, and I'm open for questions right now.
Thank you very much, Robin. Perfect timing. Do we have questions? Please feel free to just unmute and ask a question. Robin, if you can see someone who wants to ask a question that I can't, please just say so, right? I'm not very good at this Zoom business, so.
Yeah, but I don't see anyone raising a hand.
Okay, I have a question. So given Moshi's talk, what's the relationship between what you're doing and temporal logic? There's some sort of omega regularity here, right? So is it
yeah,
a fragment
so
of temporal logic?
not really. we used notations of linear temporal logic, namely the reachability property. We said we eventually reach the effect or error set. And this is LTL, an LTL formula for the Markov chain. And the omega regular property is even more broader. In our paper, we actually defined p-causes for omega regular properties, and we started from there. And we then found this reduction to reachability properties. And this is a fragment of linear temporal logic, yes.
So could you do something like a naive translation?
Not from here. Also, I'm not quite sure what the
I'm guessing that it's the
question is.
causality business that isn't straightforward, right?
So basically, we didn't define any kind of logic here. So we can't translate the logics to each other. So yeah, I think you would have to think about what kind of logic these p-causes would incur, and which fragment of the LTL logic this would be. I think it would be some kind of extension, but I'm not really sure. I've not thought about this question. It's a good question, I think.
All right. Okay. Anyone else? We've got probably time for one more question. No? Okay. Thanks very much, Robin. Is it all right if I now switch to the next speaker?
Yeah. Thank you for having me.
All right. Thanks, Robin. Cheers.
Cheers.
Stefan, you're up next. Are you ready?
Hi.
Hi.
Okay.
So Stefan, you have 25 minutes for your talk. So what I will do is I'll give you a 5-minute warning when you're at the 20-minute mark. Okay? So I'll literally just unmute my microphone and say, Stefan, 5 minutes. And if you could acknowledge that, then I just switch off my microphone again. Okay?
Perfect.
All right. We've got probably another 2 or 3 minutes, so I can't see your screen. Are you able to share your screen, or are you doing it already?
Not yet. Let me check. Now you should be able to see it.
Okay. And I pronounce your surname just Pranger?
Oh yeah, that's perfectly fine. Yes.
Yep. Okay.
Could you just confirm that you see my screen, because it says that I'm sharing,
Yes.
but I lost Zoom.
Yep.
Okay.
You can see the screen. Where are you from? What's this IAEK business?
So this is the German abbreviation of our institute. I'm from Graz, Graz University of Technology.
Oh, so Austria.
Yes, Austria. Oh yeah,
right.
Austria.
Okay. All right.
Okay, do you want me to wait until it's 3 a.m. in Graz?
Yeah, because see, there may be people that are waiting for your talk only, and it's not really fair on them if we start earlier. So it's about what, 1 more minute. So I'll just wait till then and introduce you and get going. Okay, hi everybody. It's time for our second talk in this session, and the talk is given by Stefan Pranger from, is it Technical University of Graz, did you say? I'm not sure. And he's going to tell us about Tempest, which is a synthesis tool for reactive systems. Over to you, Stefan.
Thanks very much. Hi, everybody. I'm very happy to present to you our current and still ongoing work with Tempest, our synthesis tool for reactive systems and shields in probabilistic environments. So this has been and is ongoing work with Bettina Könighofer, Lukas Posch, and Roderick Blum, all of which are from Graz University of Technology. And before I start, I want to give a big thanks to Jos-Peter Katun and especially Tim Quatman from our WTH Aachen, because they gave me a nice introduction to their model checker, their probabilistic model checker Storm, which Tempest is built on top of. Okay, before I go into the technical details and capabilities of our tool, I want to motivate what our tool is capable of. So I'm considering our environments to exhibit probabilistic inputs. So I want to start with reactive synthesis, where our task is to construct an optimal strategy for our controller, which exhibits probabilistic input from the set environment with respect to some formal specification, which is usually in some temporal logic. In what we call shield synthesis, I'd like you to consider the same situation. So we're still considering the task to construct a controller which behaves, which adheres to some formal specification while exhibiting probabilistic inputs. But this time we're now considering this controller to already be either handcrafted or the result already as the outputs from some neural network, for example. Good example, another one would be reinforcement learning. The task in shield synthesis now is to compute the most permissive strategy for the controller. So we want to be as least invasive as possible by presenting the controller with a set of correct actions from which the controller is allowed to pick an action. We distinguish between two application types for our shields. The one that you just saw on the slide before is what we call a pre-shield, and what you see on the right-hand side now is what we call a post-shield, both of which get computed in the same way, just applied differently. In the left-hand side, you see the case of pre-shielding, where we, as I already mentioned, forward a set of correct actions based on the input from the environment to the controller and restrict its available actions. Whereas in the situation on the right-hand side, where the loop contains the shield after the controller, we're going to control the, we're going to change the controller's action if the system or the controller would decide to leave the winning region. Okay, so besides this distinction between pre-shielding and post-shielding, we make another distinction between qualitative and quantitative specifications from which we synthesize the strategies. And since the construction of strategies for qualitative specification is blazingly fast, you can also distinguish between offline and online computation, where your shield, for example, could adapt to the changing behavior. And last but not least, we also distinguish between behavior that we expect from the environment, which could be purely adversarial, which could be a mixed between adversarial and probabilistic inputs and purely probabilistic behavior. In order to motivate this, I'd like you to consider a traffic light system, like, for example, a reinforcement agent that has been trained to control a small section of a city or a single traffic light, where it should set the green light. What I consider to be probabilistic behavior would be that we expect new cars arriving at that junction to be sort of uniformly distributed. And in adversarial behavior, it could be that, as you can see on the right-hand side there, the environment decides that the probability of cars arriving where already the bulk of the cars are is considered to be much higher. And this leads me to our first technical detail of Tempest, namely the two modeling paradigms that we feature. For the mentioned case of considering purely probabilistic behavior of the environment, or the average case, we model our environment and controller in Markov decision processes, which is the tuple that you see on the slide, consisting of a set of states and a distinguished initial state, a set act of possible actions that the controller can issue, and a probabilistic transition function P. And if we want to switch this over to incorporate adversarial behavior, we're now going to, what I've indicated with boxes here, introduce big gamma here, a set of players. So the definition of the stochastic multiplayer game that I'm considering here is the same as for the Markov decision process, just that we are introducing a set of players which partitions the state space such that in each and every state, exactly one player can issue the next action. And we can therefore consider one of these players to be the adversarially behaving environment. Okay, a second big building block of shield synthesis is, of course, property specification. And Tempest is able to read properties from PRCTL and RPATL for Markov decision processes and stochastic multiplayer games, respectively, where PRCTL is probabilistic CTL with rewards, and RPATL is just an extension where we took the coalition operator from alternating time temporal logic that you can see at the bottom of the slide, which partitions the game into a set of players that are part within the coalition, which want to satisfy a given specification phi, whereas players from the complement of the coalition are going to try to falsify the property. What I've put here on the slide is what Tempest is currently able to solve both for MDPs and SMGs, where you can see that this phi is what we call a state formula. So it's it's a propositional formula given over the labels that are available in the model, combined with the P-min and the P-max operator and the temporal operator until, which can either be bounded or unbounded. We can compute the probability of reaching certain states via the well-known transition of the until operator. And what I want to stress here is that these phis currently in PCTL can only be state formulas, meaning that you cannot currently nest formulas. For example, liveness properties like globally eventually is not possible yet. This would be the extension PCTL star. But luckily, as I've already said, Tempest is built upon storm. And whilst we were submitting Tempest to ATVA, the folks in Aachen have already implemented this PCTL star, so I can already foreshadow that this will be implemented into Tempest as well, and so shielding will be extended to incorporate PCTL as well. Last but not least, we are also able to use one reward-based property with the Rmin or Rmax operator, where we're currently able to compute long-run average values. But this is not enough semantics to introduce our shields or to compute our shields. And that is why we extended both PRCTL and RPATL with what we call shielding expressions. And such a shielding expression will consist of a file name where the most permissive strategy is to be written to, a shielding type pre-safety and post-safety, which compute the pre-shields or post-shields that I mentioned at the very beginning, or it could be optimal, where an optimal post-shield is to be computed. And we also need a relative comparison value lambda or an absolute comparison value gamma. And based on these, Tempest will construct these most permissive strategies. So Tempest will construct these most permissive strategies sigma I, which will point from each state of the model to a set of allowed actions. And such an action AI will be in the set alpha, depending on either a relative or absolute comparison. If we want to maximize the probability of satisfying the formula phi, we compare each of these actions AI. So we compare the expected probability of satisfying it with the relative value with respect to lambda and the probability of satisfying phi for the best performing action, which is depicted with a star here. So we would usually pick lambda, which is near to 1, such that you get a small interval of the best action and some actions that are still almost as good performing as the best action. And vice versa, if you want to minimize the probability of satisfying phi, then you take 1 plus a very small lambda, such that you get the best performing action and some that are have a bit of a higher probability. And if you use an absolute comparison, it's relatively easy to describe this. The probability of an action to fulfill phi will be compared to this absolute value. And if it is larger, if it is greater, equal, or lesser equal, it will be in the allowed actions. And a small remark here, this can of course introduce deadlock if these values are too high or too low. So I've got some example specifications here. The first two of which are for MDPs and SMGs respectively, and they basically cover the same they basically cover the same specification. So given this warehouse example that you've got on the right-hand side here, where two robots are they're picking up packages or whatnot, and they want to avoid crashes. So we want Tempest to synthesize now a strategy such that within 7 time steps, we can ensure that no crashes happen. The small remark here, since with SMGs, we're introducing states for the adversarial player as well. We're basically having half moves here. That's why the factor of 2 is here in combination with the globally operator. So these two specifications would construct a strategy. in the sense of reactive synthesis, whereas the last two ones prefixed with our shield expressions will construct, in the first example, a pre-shield with a relative comparison value, and in the second version, a post-shield with an absolute comparison. So to summarize our main contributions here, we've built a highly efficient tool, Tempest. Because it's built on Storm, we can use the highly efficient algorithms that are already implemented in Storm, and we've extended those with the modeling paradigm for games. So Tempest is able to synthesize controllers for games, and we've also built a shield synthesis framework for Markov decision processes and SMGs, and both of which have a very strong emphasis on legibility of the resulting strategies. So very quick, how do you use Tempest? Tempest is a purely CLI application, so there is no user interface, and you can call it via this CLI call here, where it will construct first the state space described by the model file, and then it will compute and synthesize strategies for all shielding expressions that are given within the property list. And in order to increase legibility, you can also ask it to completely describe all the labels of the states and give you the names of the choices or the actions that are available in the model. And if you want to construct the controller in terms of reactive synthesis only, you can append the export scheduler command. And now to some results and as an example to show you how these shielding outputs, what these shielding outputs look like. I've got the very same example here. Now in the actual syntax, how you would define it in the property file, where you have got this warehouse example, where I've picked a width of 3 for the abstraction for the grid. So you would need to think of this now having only one row of these shelves. So it's a very narrow warehouse. And we want Tempest to compute the shield in a game setting for the shielded robot, such that for 3 time steps, the probability of reaching a crash is minimized. And I've picked I picked 2 states and constructed a pre-shield and post-shield in order to show you the comparison and what the output would look like. So you've got these same 2 states here, prefixed by their ID, and you can see that these 2 robots are basically 2 cells apart from each other. And since we're in the game setting, the other robot is behaving adversarially, meaning that moving towards the robot will not yield a minimal probability of not crashing into it, meaning that the shield has restricted us to moving to north. Whereas in the second state, everything is okay since we're a good distance away from the other robot. And you can see this copied over into post-shielding setting, where if the controller would have picked the deemed unsafe action of moving towards the other robot, we would have overwritten it with actually moving to north. So what are the times for constructing these strategies? So in the paper we feature a broader range of experiments, and we've compared ourselves with Prism, which is one other probabilistic model checker which can model check with stochastic multiplier games. And what is interesting with respect to what I've shown you on the slide before is that our safety shield construction, which is the blue plot, fares way better than the safety synthesis when done with Prism. We've also compared ourselves with respect to some qualitative synthesis.
Stefan, 5 minutes.
Yes, thanks. Where we have remodeled the situation of controlling such a traffic light and compared it with a CAF paper from Avni et al. And we can see that our tool fares way better. So the tool is currently available under this URL, and you can also go to this QR code if you'd prefer. And on the website, under examples, we give a more in-depth and detailed discussion of the examples that we have in our paper. And since we've got some time, I actually want to switch over and show you some applications of our shields. So what you can see here is like a novel approach to the game of Snake, where both of these snakes have the task to pick up their apples, and as you can see, whenever a snake comes to a crossing, you can see sort of a traffic light indication. And whenever such a snake enters a corridor which leads to a crossing, you can briefly see that the video stops, and this is where for part of a second, Tempest is computing a safety shield such that these two snakes do not crash into each other. And as another example where we have used qualitative shields, which have been computed online, we've got this example here of controlling multiple traffic light systems in an abstraction of Helsinki, where you can see that the reinforcement agent here is being forced into territory where he's not been trained with, mainly because this road is blocked here, and we have in a fixed interval recomputed our qualitative shields such that the waiting time for cars is to be reduced. And in these fixed intervals, we have recomputed the shields, and we can see that in our shielded version, a bulk load of cars can be reduced. Okay, and with that, I want to come to a conclusion and future work. So as I've already said, we are interested in extending the capabilities of our tool to more complex properties. And as I've already said, PCTL star is something that has already been implemented in Storm. So this is where we're going to go next. And also from a theoretical point of view, RPATL star, so the extension for games with more complex properties, is of interest for us. Besides the model checking approaches, so the capabilities of our tool, we're also interested in improving its usability as a synthesis tool. So plain and simple, it's currently exporting everything as plain text files, and we want to improve the legibility even more of our output, and maybe even make it as an interactive tool. And since Markov decision processes and stochastic multiplayer games aren't the only probabilistic models out there with non-determinism, we also want to extend our modeling capabilities with concurrent stochastic games. Thanks very much, and I'm very happy to take your questions.
Okay, thank you, Stefan, for an excellent talk. Questions? Please just ask. Okay, Stefan, I have a question regarding scalability. So if you went back to that, that snakes game,
Yes.
what happens as the number of snakes increases? So you go to 3 snakes, then 4 snakes. Will you see an exponential slowdown?
So the issue more at hand, as I would say, is that you will most certainly experience that. As you've seen in my slides, I have not used an unbounded temporal operator, meaning that if you were to use unbounded operators, every probability in there would converge to 0 or 1. So if you were to put in more and more snakes, you could just limit the time horizon that we're looking into the future. I'm not sure which time horizon we've looked at here. So this is certainly something where you can work against that scalability issue. But I would not be concerned even if you were to put in more and more snakes. As you saw, these have been computed online, and as I said, the game stops for a brief second, and I don't know whether this is whether you can really see that via Zoom, but it's maybe 1 or 2 frames where it stops, so I'm not really concerned about scalability.
And so then on your next example with a map of Helsinki, how many cars were there? Or isn't that relevant? Is the number of cars relevant?
Not really, because we have a cutoff. I've not mentioned that. So we are not computing. So if we were to take every car into account, that would mean that we would basically have an unbounded model. So the cutoff is very small, but it's reasonably big to make a difference in the decisions that the shields take. So there are a lot of cars. I can't really count it, but since we're cutting it off anyway, it does not make a difference.
So it's actually realistic, right? It's a realistic example here.
Yes.
Yeah.
I mean, the thing the thing that we're lacking is the ability to actually count cars at a traffic light, like at junctions, I would say. So we would need to be able to count how many cars actually are waiting, and I guess this is currently only binary. So I know of some induction-based technology where you can decide whether there is a car or there's not a car waiting. But yeah, this would definitely scale.
Okay, thank you, Stefan. I might just
Thank you.
stop you there and see if our next speaker is available. Let me just see, who is it?
Yes, that's me.
Who is our next speaker, please?
Hello. Yeah, I'm the next speaker. Can you hear me?
Yes, I can hear you. Can you tell me how to pronounce your first name?
Zixing.
Xixing Huang.
Yes.
Xixing Huang. Okay. And what university are you from?
University of Illinois at Urbana-Champaign.
Okay. Could you please share your slides with us? I can't see the slides at the moment.
Yeah, can you see the slides?
Yeah, we can see it now. So, Xixin, what I'll do is you have 25 minutes for the talk. And so what I'll do is I'll interrupt you at the 5 minutes from the end mark, and I'll just say something like Xixin 5 minutes. And if you could acknowledge that, then I know that you know, and so on. Okay?
Sounds great.
All right. Where are we? We're almost there. So hello, everybody. We're back for the third talk in this session. The talk is being given by Xixin Huang from University of Urbana-Champaign. And she's going to tell us something about automated quantized inference for probabilistic programs. Over to you, Xixin.
Okay. Yeah, so today I'm going to talk about our work ATVA, which does automated quantized inference for probabilistic programs. This is a joint work with Saikat and Sasha. We're all from the University of Illinois at Urbana-Champaign. First, what is probabilistic programming? Well, it is a way to represent a statistical model in the form of a program. Like here, we have a statistical model like this and a bunch of data. We want to feed this model to the data to get the distribution of the variables. To do that, we can write this 4-line program, and we can use some probabilistic programming system to automatically solve this model. These probabilistic programming systems include this work, ATVA, and many others like STEN, SCI, and SPPL. They are going to output the distribution of the variables in the program. And this has many important applications, like in self-driving, people use it for object detection, and it is also used for locating in map applications. And more recently, people use it for predicting COVID cases to help people fight with COVID. Now, let me give an example of a simple probabilistic program, and let's see how ATVA deals with it. At the beginning, the program specifies 2 priors, A from a uniform distribution from -10 to 10, B also from a uniform distribution from -10 to 10, and we want to know what is the joint distribution of A and B. And on the right-hand side, I show ATVA's result, which is a joint distribution of A and B. It looks very uniform. And if we have an observation, 3.4, we can write this observe statement to specify that 3.4 is from a normal distribution with mean A plus B and variance 1. And ATVA is going to give us the joint distribution of A plus B given this observation. So the distribution looks like this. There is a density concentrated in the middle, and the cross-section looks like a normal shape. Now, if we have 40 data observations, we can write the observe statement in a for loop. And in the end, we can return A and B to query about the joint distribution of A and B. And on the right-hand side, here is ATVA's result. ATVA is able to finish this program within 0.8 seconds, which is quite fast, and it is by applying 200 speeds per variable. So remember that ATVA does quantized inference, so when you see these small little grids on the plot, those are due to quantization. On the contrary, here is STANDards result. STANDards, if we run STANDards for the same 0.8 seconds, it is only able to finish around 7,000 to 8,000 samples. And there are some areas in A and B's domain that it hasn't explored. But ATVA is able to give us that on that area, there is a low probability, and that probability should be greater than 0. More importantly, ATVA's result is closer to mathematical expression, and STAN's result is just a closer approximation. So what is ATVA? ATVA is an inference algorithm works on probabilistic programs with continuous posterior distributions. We define it as a static program analysis. We'll see it later. And ATVA does quantized inference with interval and density cubes. Quantized inference means it discretized distributions with piecewise linear interpolation to approximate the original continuous distributions. Quantized inference sidesteps the problem of computing intractable integrals. And ATVA's results have formal guarantee on convergence and error. We show experimentally the result is accurate for many benchmarks. We'll see it later. Now, let me show how ATVA's static analysis works. So if you are wondering what is this 3D plot I keep showing, it is just a visualization of our abstract state. Our abstract state has two components. One is the interval cube. You can imagine those are like the x-axis ticks and y-axis ticks on this plot. Correspondingly, there is another density cube in our abstract state that stores the z-axis value corresponds to each A value and B value. Okay, so if for this element 0.025, it corresponds to, it is on the first row, second column. So it is corresponds to the second element in A's interval cube and the first element in B's interval cube. Specifically, this means we use the density as the lower bound when A is equal to -5, B is equal to -10 to approximate the density of the whole interval when A is in -5 to 0, B is in -10 to -5. And intuitively, our abstract state is just a quantization of the concrete density function, so that the interval cubes are like the quantization of F's domain, and the density cube is like the quantization of F's codomain. And if you are wondering why the summation of the density cube is not equal to 1, it's because that our density cube stores the density instead of the probability. Now, with this in mind, we can do a step-by-step analysis. At the beginning, we initialize our density cube to be 1 because the concrete density function is also 1. And if we see a prior A from uniform -10 to 10, in our interval cube, we are going to split the domain of A into 4 equal length intervals. So this is just for an example. Due to the space limit on my slide, I just show 4 intervals, but in practice, we may use many more intervals. And correspondingly, in the density cube, we also have 4 elements, and each of them corresponds to one of the lower bound in the interval cube. Similarly, if we have B from uniform -10 to 10, we can also split B's domain into 4 equal length intervals. And to calculate the density cube, we do the product of the individual density function to get this 2-dimensional density cube. So that this element on the first row, second column corresponds to the second interval in A's interval cube and the first interval in B's interval cube. If you are wondering why B has a different dimensions than A's interval cube, just imagine that our abstract state is a quantization of the concrete density function. So just like I'm showing on the plot, A and B are on different axes, so that our density cube is able to store the z-axis value for all the possible combination of A and B values. Now, if we have a likelihood statement like this, we first need to resolve the expressions A plus B. Here we do a simple summation of the intervals to get this A plus B interval cube. For example, the first element in A plus B's interval cube corresponds to the first element in A's interval cube and the first element in B's interval cube, so that there is a 1-to-1 correspondence between the interval cube and the density cube. Now we can deal with this observed statement. To do it, notice that our concrete density function should be the prior, which is 0.0025 times the likelihood, which is normal PDF 3.4, given A plus B and 1. We simplify the notation, and in our density cube, it is the same thing, 0.025 times lowercase l, but we replace A plus B with the value as the lower bound of the interval cube. To understand why this is correct, remember that our abstract state is a quantization of the concrete density function. So A is like the x-axis ticks, B is like the y-axis ticks. So P stores the z-axis value corresponds to each A value and B value. So this value in L is the lower bound of A plus B's interval. Now, if we have 40 observations, our concrete density function will become 0.025 times the product of 40 known PDFs. In the density cube, it is the same thing, but we replace A plus B with A plus B's lower bound. And remember, our abstract state is a quantization of the concrete density function. So still A plus B are like X and Y axis. And the P stores the Z axis value corresponds to each A and B value. So in the real case, we need to resolve the for loop step by step, but here I just want to show the final result. And what I've talked so far is that our abstract state is a quantization of the concrete density function, but reversely, we can do a piecewise interpolation on our abstract state to get an approximation of the density function. Like here, we can create piecewise function based on the result abstract state to create approximate f hat. And in the concrete domain, we need to calculate the posterior like this. Similarly, in our abstract domain, we do the same thing, but based on the approximated f hat to get the posterior approximation p hat. So the key is the integrals over f, which is continuous density functions, are often intractable, but with p hat, we can always integrate by summing over piecewise linear segments. And what I've talked about is on 2 variables, but actually ATVA is able to deal with many more variables. And here I want to give our main theorem, which says that on a bounded domain C of the variables, by applying sufficiently many states, random variables following ATVA's posterior approximation p hat will converge in distribution to the true posterior p. So what this intuitively means is that by applying sufficiently many speeds at certain value of the variables, p hat will be equal to p. And let me give a summary for what we've covered so far. The ATVA is an inference algorithm, works on probabilistic programs with continuous posterior distributions. ATVA does quantize inference with interval and density cubes. ATVA's results have formal guarantee on convergence and error. You can see the paper for details. So you may be wondering what is this bounded domain that I mentioned in the main theorem. So for example, if we have a variable I that is from uniform distribution from -10 to 10, we can set the bounded domain to be -10 to 10 because we don't need to care about the area outside of it because the probability is always 0. And if we have this bounded domain, we can do the quantization by splitting this bounded domain into many intervals and do our analysis. But you may be wondering, what if we have a normal distribution that can extend to infinity? How do we choose a bounded interval to do finite number of splits and do our quantized analysis? To deal with this problem, we come up with this adaptive algorithm to help us automatically choose a bounded domain. So instead of going through this algorithm due to the time limit, I'll just show an example to give you some intuition how this algorithm works. At the beginning, we get the initial bounds from the priors in the program. For example, if there is a variable I following normal 0, 1, we can set the bound to be -50 to 50, which is a very large interval that should cover most of the density in the prior. And we do the analysis on this large interval, but find out that the result is not very accurate. In this interval, there's large part of it has probability close to 0. So we can adapt this interval to let it focus on areas that has larger density, that is -10 to 10. And we do the analysis again, but we still find that there's large proportion in our interval that has very low probability. So we shrink our interval again and again until a point that our bounded domain Ci that has probability that is always greater than some threshold. Then at this point, we can apply many splits in this bounded interval to get a quite accurate result. And this algorithm is just based on heuristic, and we don't have any formal proof for it. But in our evaluation, we can see this algorithm that adaptively choose the bounded domain works better than any hand-tuned bounded domain. And so far I've talked about our algorithm. Let's see our evaluation. So we evaluate ATVA on 24 probabilistic programs from existing literatures. We compare ATVA with STAN, Sci, SPPL. We implement ATVA in Java with ND4J library for tensor computation. And we run all experiments on this machine, which is not a fancy supercomputer, but ATVA is able to finish everything fast. We can see it later. So this is our metric we use to measure the error. We use this common groups near null statistic. For each variable x, we calculate the supreme of the difference between the true CDF that we manually derived and the approximate CDF that we get from the approximate algorithms. For example, in the previous example, we have the standard result and ATVA result. We first integrate the other variable b out to get the posterior of a, and then we calculate the CDF by integrating p hat, and we compare it with the ground truth that we manually derived. To find the KS statistic, we find the maximum difference between these two lines. For example, here STAN has KS of a equal to 0.05. We can do the same thing for ATVA, but I just don't show it here. So there are 2 points I want to mention about KS statistic. KS is able to compare sample distribution with analytic solutions, so it can help us compare STAN's sampling result with ATVA's result to do a fair comparison. And our main theorem for ATVA states that ATVA is guaranteed to converge to, ATVA's error will converge to 0 with sufficiently many splits. And there are our benchmarks. We have 24 programs from different literatures, and these include 3 mixture models for Bayesian networks, 11 linear and nonlinear regressions, one-time series, and many others. And we have many different distributions and model structures in our program. Here I show with a plus. I use plus to show the mixture of two distributions, and I use product to show the posterior is calculated by the product of this distribution's density function. And our data sets range from 0 to 100, and the number of random variables range from 1 to 102. There is an optimization we described in the paper that help ATVA to scale on programs with large number of variables. You can see the paper for details. Now let's look at the results. Let's look at it one by one. So this work, ATVA can finish 20 out of 24 programs within 2 seconds, which is quite fast. And the error is very small. It is at most 2% error in the CDF. When I show with a pink color, it means Aqua takes longer than any other algorithm, but here we don't see many pink colors. Now let's look at STAN, which does approximate inference. We use two different STAN algorithms, STAN-VI and STAN-NUTS. In the time column, I show the time to reach the same error or accuracy as Aqua. If it cannot reach the same accuracy level of Aqua, we note down the time for 400,000 iterations where STAN has guaranteed to converge. And
STAN 5 minutes.
Okay, thank you. So STAN-VI is faster and its error is quite large. It can be up to 34% error in the CDF. I show with pink color that when it is worse by Aqua by at least 0.01, there are many such pink colors in STAN-VI's column. And we can see STAN-NUTS. STAN-NUTS takes longer. The average time for STAN-NUTS is 77 seconds, and its error is slightly larger than Aqua's error. Also, we show with pink color when it has larger error than Aqua. Now let's look at the exact inference algorithms. We have two of them. Because the error is 0, we omit the error column. Psi is slow with many timeouts, meaning running it takes more than 20 minutes to run, and many times it results in unsolved integrals. STPL is relatively faster, but it cannot work on many programs. It is because SPPL doesn't support transform variables in factor statements, which is a necessity for many these real-world programs. So here I want to show some results from STAN-NUTS and Aqua, and I want to give some insights when STAN-NUTS may fall short and when Aqua can take an advantage. So first, when there is a mixture model with mixture modes with different density groups, STAN-NUTS may ignore one of those groups, but Aqua can correctly capture both groups. And if there is non-differentiable distributions, STAN-NUTS is not very efficient on them. And if there is variable symmetries, STAN-NUTS doesn't work well on programs with variable symmetries as stated in the following paper. And if there is a robust model with complicated posterior to sample from, STAN-NUTS cannot be very efficient, but Aqua can give much better result. So give a short conclusion. STAN does approximate inference based on sampling, but it may not be accurate. And there is Psi, which does exact inference, but it is slow, and many times it may result in unsolved integral. And there is SPPL, it's relatively faster, but it is not applicable to many models. So in this work, we propose Aqua, which does quantized inference to be more accurate than sampling and scales better and solves programs out of reach of exact inference. To conclude, so Aqua is an inference algorithm working on probabilistic programs with continuous posteriors. Aqua does quantized analysis that has formal guarantee on convergence and error. Aqua has an adaptive algorithm that automatically refines the granularity of quantization. Our evaluation shows that Aqua is more accurate than approximate inference and supports programs out of reach of exact inference. And Aqua is open sourced here. You can download it, play with it, and give us some feedback. So that's the end of my talk. Welcome to questions.
Okay, thank you, Shixin, for an excellent talk. Questions?
Thank
Anyone? No? Okay, I have. Shishin, could you please go back to when you showed that how you calculated the matrix, the P matrix?
Oh, I see.
In one of your earlier slides where,
Yeah. Let me go back to it. Like here.
yeah. So here you're always using the under approximation, right? The lower bound.
Yes.
Now, I don't know anything about the technical details of statistics or what you're doing here, but why the lower bound? Why not the upper bound?
Yeah, we can also use the upper bound. So or the midpoint. Just for easy formalization and explanation, I use the lower bound here. But actually, in the implementation, we have we also have the upper bound. Like it is not only at the lower bound, we store all the bounds from -10 to 10. So if you like, or if the user likes, they can configure it to make it the upper bound or the midpoint, and it doesn't change the result, and our convergence theorem still holds. It's just for convenient description and explanation.
Okay, so then wouldn't it make more sense to do interleaving, where you do a lower bound and then an upper bound, a lower bound and then an upper bound, a little bit like a binary search? So you under approximate and then you over approximate?
So
that should also converge, right?
So it may not be under approximation, as those lower bound, we are calculating the exact value as the lower bound. And the lower bound of the next interval is the upper bound of the previous interval. So it may not be an underestimation. But if you want, you can select those interval in any way you want. Just we prove our guarantee is on those equal length lower bounds. But if I'm not sure if you use other ways to select the intervals, how does it look like? But yeah, it can be quite interesting to try.
No, so I'm not suggesting other ways. I'm just saying you have one way, which is you pick the lower bound and it works, right? Then you confirm that choosing an upper bound uniformly would also work. So then my suggestion is that you alternate. You do once, one run or whatever you want to call it, you do with the lower bound, and the next one you do with an upper bound, so that you're squeezing the exact answer from both sides, so to speak. I mean, perhaps it doesn't make sense, but
so here our it's like our lower bound of the next interval is exactly the same of the upper bound of the previous interval. So
oh, I see. So then swapping doesn't make any sense. Okay, no, I get it.
There is no difference between them.
Yep. Okay. Anyone else? No? Okay, I have another question. Can you go to the main theorem where you said something about convergence?
Yeah. Okay.
Can you quantify sufficiently many?
When it's going to infinity, like we have infinity splits, then p hat is equal to p, something like that. So there is like a asymptotic convergence. When the number of splits goes to infinity, we have the p hat equal to p for all the value of variables.
Okay. Because see, what I'm thinking is, if sufficiently many means you have to wait till the end of the universe, that's not much good to me, right? But you know, but your practical, your experimental results are good. So what I'm wondering is whether you can sort of, I don't know, tell me more about how big sufficiently many splits has to be, given some parameters of the problem.
So like in the previous example I'm showing, like here we are taking 200 splits. On this plot, it is this plot is generated based on 200 splits, and you don't even see any quantization error because 200 is already a large value, at least for generating this plot. And it is able to finish at everything within 0.8 seconds. So even if you increase this number of splits to like 10,000 or 100,000, it will finish in several seconds.
Okay.
Yeah.
All right.
So,
any other questions? Oh, go on. Yes, go on.
So it's like the complexity will increase linearly with the number of splits.
Okay, that's what I was after. Yep. That's what I was after. Yeah. Okay. Any other questions?
Hi, can I ask a question?
Sure.
It's more on the application of this wonderful tool. Could you please go back to your motivation slide? I recall that you say this can be used for like, this slides, auto driving car. So correct me if I understand, is that if we have some prior, estimation of what is the environment, and then we have some likelihood, then we can infer what is the posterior, right?
Yes. Yes.
So that's the exact application of this tool in this particular example, right?
Yes. And yeah, go ahead. You finish your question, then I can.
So, but in that case, would this posterior be what kind of does it requires a lot of number parameter to describe this posterior?
Depends on the model, like depends on the application, like, or depends on the user, how the user writes the model. So yeah, it really depends. So in our examples, there are variable number ranging from 1 to 102. So yeah.
I mean, so you're saying that 100 is like 100 mixture of the Gaussian, something like that, right?
Yes, you can think that way. Yeah.
Okay, I see. So basically, it's any distribution, you can always try to approximate using a mixture of Gaussian. Depends on how many mixture of Gaussian you choose. Let's say 100. So you will be able to generate this 100 Gaussian mixture.
So it's not like we are using a mixture of Gaussian to approximate. We are using quantization, like we split the posterior domain into equivalence intervals or cubes. If it is if there are 3 variables, there will be a 3D cube that we split the space. If it's a 2D, we'll have these squares. I don't know if this answers your question.
Yeah, exactly. Let's say, okay, the problem domain has many dimensions. Let's say 1,000 dimensions.
Yeah.
So how will I use this tool in this case?
So the result will be, theoretically, the result will be the joint density of the 100 dimensions. So it's trying to model the correlation of all the 1,000 dimensions. We can also integrate out other dimensions to get a marginal distribution of one dimension. Depends how you want to use it. So we can provide the joint distribution of the 1,000 dimensions, and we can also provide the marginal distribution for one dimension by integrating out other variables or other dimensions.
Oh, I see. Okay, cool.
Yeah.
Okay, any
Thank
other
you.
questions? No? Okay, thank you very much, Shishin. And I think that's the end of this session, isn't it?